Okay, so it gives me great pleasure to introduce today's speaker, Dan Weisz. Dan is an assistant professor at UC Berkeley and an expert in near-field cosmology and the study of dwarf galaxies as probes of fundamental physics, for instance, reionization or the nature of cold dark matter. So Dan started working on dwarf galaxies during his PhD at the University of Minnesota, and there he used HST data to study star formation of dwarf galaxies. In 2010, he moved to the University of Washington to work on the panchromatic Hubble Andromeda Treasury, which is a study of M31's star-forming disk and its population of star clusters. And then in 2013, Dan began a Hubble Fellowship at UC Santa Cruz before a brief return to the University of Washington, and then joined the faculty at UC Berkeley, I think in 2016. So Dan has numerous achievements. Most recently, he was awarded the Newton-Lacey Pierce Prize in Astronomy from the American Astronomical Society for outstanding achievement in observational astrophysics. And Dan is also the principal investigator of the Resolve Stellar Populations Early Release Science Program for JWST. So today, Dan's going to tell us about an ongoing HST Treasury program to map out M31's satellite population in 6 dimensions. So thank you very much, Dan.
Great, thanks for having me. Let me just share my screen here. All right, great. Well, so today I want to just talk to you about some of the work that I've been doing recently, primarily around M31, but I really wanted to start and give you the backstory of how we got to thinking about M31 as what I would call the next frontier for low mass galaxy formation. And so this all starts for me with an image, something like this. For many astronomers, your eyes are drawn to the beauty of the Milky Way and its dust lanes. But for me, they're actually drawn to the smaller smudges in the sky, the LMC and SMC, and we've known about these galaxies for centuries. But really what they are is they're the tip of the iceberg of this whole ecosystem of even lower mass galaxies. And this figure from a recent review article by James Bullock and Mike Boylan-Colchin gives a sense of what the dynamic range is of the type of dwarf galaxies hosted in the local group. So in the background is the LMC, and you can see for scale, it's about 10 kiloparsecs across. And then you can see this variety of other dwarf galaxies, satellites such as Fornax, Draco, and PIC1, just spanning this whole range from fairly massive down to, well, very, very piddly and tiny. And we now know of nearly 100 of these in the halo of the Milky Way. Of course, the data hasn't always looked this good. And just to give you a sense of where this started, let's rewind the clock a few decades. This is a hand-drawn stellar density field of Sculptor, which is the first faint Milky Way satellite that was discovered by Harlow Shapley in 1937. Interesting side note that they actually think they found it in 1908, but it was just attributed to a calibration issue, and it was rediscovered, I guess, in 1937. And he painstakingly drew out all the stars by hand here. And this is really where our understanding of, I think, low mass galaxies began, because it was really the discovery of these satellites that spurred on a lot of science. So this figure from Josh Simon's recent review article encapsulates sort of the discovery of dwarf galaxies around the Milky Way, many of which Cambridge played a leading role in finding and characterizing. So what we're looking at is just the calendar year versus when galaxies were discovered. And you can see basically through the year 2000, there were about 13 discovered, almost all via photometric plate surveys. And to give you a sense of what people were doing with this data and what their questions they were asking, we can also look at some of the work that Paul Hodge, who is at Washington, did during the 60s. Paul unfortunately passed away last year, but leaves a huge legacy in this field. And so Paul, in the 60s, took photographic plates of a lot of these dwarf galaxies, and then by hand drew these density contours just to understand what the structural parameters were. You can imagine how difficult and painstaking that work must have been. And then just for comparison, I'm showing in the bottom panels these stellar density maps measured from CCDs by Mike Irwin. And you can just kind of compare the two. If you compare Paul Hodges' Draco to Mike's Draco, you'd actually say that Paul did a pretty good job. Same with Fornax or Saminer, etc. And many of the questions surrounding the classical dwarfs for decades were are they as old as the galaxy? Are they the building blocks of the galaxy? How did they get their populations? How did they lose their gas, etc.? And I think what, in my view, transformed this field into more of a cosmological field was really the missing satellites problem. I think there was some discussion of dark matter and dwarf galaxies prior to this, but I think this really encapsulates one of the important issues in this field. And so this is a figure from Ben Moore's 1999 paper, which on the y-axis is plotting the cumulative number of halos or galaxies. And on the x-axis is their circular velocity, or equivalently their mass enclosed. And there's a lot going on in this plot, and I just wanted to highlight a couple of things. One is that if you pay attention to just the dashed line, this is the expected number of dark matter halos around a simulated Milky Way galaxy, so around an analog of the Milky Way. And what's being shown as data points are the real Milky Way satellites. And so you can just see by comparing the real galaxies to what's expected in the simulation that there's this gap, which is roughly orders of magnitude, 2 orders of magnitude. And this is really the genesis of the missing satellites problem, that we just didn't have enough satellites around the Milky Way. And this led to a lot of discussion of what could be causing this tension and its relation to cosmology and potentially the early universe. So, one of the things that also happened around this time were the advent of the digital sky surveys. And so we now basically circa early 2000s had not only access to these classical dwarfs, but through digital surveys, we now discovered fainter systems, and the number increased pretty rapidly. So just for reference, Sloan started discovering galaxies around 2005, and DES has become a major player in this field in the south, such that we're now up to 60 or 70 satellites around the Milky Way. And so things like the missing satellites problem, for both observational and theoretical reasons, some claim are less of an issue. And this had to do a lot with work that, again, many people at Cambridge have been doing over the past couple of decades. Also note that concurrently with the discovery of these faint satellites, Keck Deimos began operation in 2002, and this has been a very powerful telescope for measuring velocities and stellar chemistry in many of the satellites. Similarly, the ACS, the Advanced Camera for Surveys instrument on HST, also came online in 2002, and it's been great for measuring ages and also stellar chemistry in many of these systems. So really, the confluence of theory, of the discovery of these faint systems, and powerful technological improvements just really revolutionized this field around the turn of the century. So some of the challenges in this field, as I described, are the missing satellites problem, and this has to do with too many model halos, dark matter halos relative to known Milky Way satellites. There's something called the core cusp problem, which basically talks about the central densities, the profiles of dwarf galaxies, and whether they're very steep and are what they call cuspy, or whether or not they're less dense and have cores. And then more recently, something called the too big to fail problem, and that model halos are too dense compared to real galaxies. And I would argue that the preponderance of the evidence of whether these are crises or not has maybe not changed dramatically in the last 20 years, though we have a lot of new data. I think the interpretation is still, a little unclear, though that's probably a good chat to have over a beer sometime. And there's a number of common solutions to all these problems that people can invoke, that perhaps dark matter is not cold, so you suppress the power spectrum as dark matter becomes warm, or self-interacting dark matter may be able to create cores. Baryonic feedback can affect dark matter density profiles. Cosmic reionization can suppress star formation and galaxies, and so you can, for example, just have empty halos without any stars simply due to reionization. Or that the dark matter mass of the Milky Way is uncertain enough that maybe there are fluctuations by factors of 2 or more, and that could resolve the missing satellites problem and other of these issues. And so I think that many of these are still contemporary questions we're talking about today, despite them being posited, almost 20 years ago, because they're difficult problems to solve. Some of the questions I've become more interested recently are even broader, which is this: are the Milky Way satellites, where we're tuning a lot of this science, are they really representative of low mass galaxies in general, or satellite populations in general? Or perhaps we're just over tailoring our understanding of low mass galaxies to fit the properties of the Milky Way satellites. And this could be problematic, because if we're trying to understand, for example, the missing satellites problem, and our system, our halo, is not representative, then we're not really thinking about this broad question. We're really just solving a problem of the local accretion history and properties of Milky Way, of the Milky Way halo. So very recently, there has been some work to extend our understanding of whether or not the Milky Way is representative, the Milky Way and its satellite systems are representative to the broader local volume. And so one example are results from the SAGA survey led by Marla Jiha at Yale. And this is a plot from her recent paper, which is showing on the y-axis the cumulative number of satellite galaxies as a function of their absolute magnitude for a number of Milky Way analogs within 10 or 20 megaparsecs. And just for reference, the black dashed line is the number of Milky Way satellites, and the gray dashed line is the number of M31 satellites. And then each of the colored lines are for a different Milky Way analog. And you can see that there's broad dispersion here, such that not all the Milky Way analogs have the same number of satellites. Of course, this isn't a surprise. It could be consistent within Poisson noise. The surveys simply just don't go down faint enough to push past this regime yet, although I think I'm optimistic we'll be headed in this direction soon. But perhaps the more interesting statistic is that of the satellites discovered by SAGA, 90% are star forming. And so that's very different than what's happening around the Milky Way, where basically everything is quenched. And this is a much harder thing to reconcile by Poisson statistics or something like this, because our understanding of satellites is they shouldn't survive in the immediate vicinity of a massive galaxy for a long time and remain star forming. And so this large fractional difference is difficult to understand in terms of our knowledge of Milky Way satellites. And so this is already just hinting that maybe we need to think about pushing our understanding of low mass galaxies beyond the Milky Way halo. The challenge, of course, is that everything is distant, and these are just integrated magnitudes, but what you'd really like to know are more detailed properties of the systems, and you'd really like to know if the formation history of a particular halo is what's influencing things like the luminosity functions and the quenched fraction. And so this is where my own work on resolved stellar populations comes in, because the resolved stars of a galaxy encode its formation history. So this is an image from the LMC that I showed you earlier. And what many people, don't appreciate about this are all these individual points are stars in the LMC, and they all provide some age information about the LMC, and the similar argument can be made for basically any galaxy that you can resolve into stars like this. So how do we get that age information? And I'll spend a little bit of time describing that before coming back to the question of what we're learning from this. This comes from color magnitude diagrams, or CMDs. So what I'm showing here is a simulated CMD in HST filters. So 475 is roughly G band, 814 is roughly I band. And this figure is meant to just orient those whose stellar evolution needs a little bit of refreshing. So if I now overplot many of the commonly known sequences of stellar evolution, such as the main sequence, so these stars in the upper left are the luminous main sequence. To the right of them are these core helium burning stars, which are post main sequence stars for fairly massive stars, greater than about 5 solar masses or so. As you go to fainter magnitudes, you have red giant branch and horizontal branch stars, and even fainter magnitudes, you get the lower main sequence. And there's this feature here, which I'll come back to, called the main sequence turnoff, which is particularly age sensitive. Just another way to show the same diagram is we can color code all these synthetic stars by their age. And so here I've retained all the stellar evolution labeling, but now you can see where there's age information. So if you're interested in very young populations, you can see that this comes from the upper part, primarily from the upper part of the CMD. And then as you go fainter, you can learn about older populations. So for example, the horizontal branch contains information about very old stars, and this so-called red horizontal branch about slightly younger stars. The red giant branch is an excellent tracer of metallicity, not so much of age, just because a lot of things overlap here. But this main sequence turnoff feature, you can see this is where there's a lot of age information. So this is the turnoff and subgiant branch. And this is where we can gain a lot of age information from resolved stellar populations. And so, going beyond just looking at diagrams like this, we can quantify the star formation history, or essentially the age distribution as a function of a galaxy, age and metallicity distribution as a function of the galaxy properties, by modeling the color magnitude diagram. So this animation is going to show how the connection between the CMD and the star formation history. So what's being shown right now in the right panel is if there was a burst of star formation in the very early universe, this is the color magnitude diagram you would see today. And this animation will populate the will populate a star formation history, and at the same time populate the CMD, just to show you what that connection looks like. So you can see we're moving progressively to younger ages in the star formation history, and you can see that the CMD is populating. And of course, in reality, what we're trying to do is we get a CMD without any age labels, and we're trying to back out the star formation history. And this is this field has been developed over the last 20 or 30 years and has become very mature, where you quantitatively can reconstruct the star formation history from the CMD. And I'm not going to get into too many of the technical details here, but I'd be happy to answer questions about that aspect later. Instead, I just wanted to show you an example in practice. So the image on this screen is of IC 1613, which is an isolated dwarf galaxy near the edge of the local group. And a number of years ago, we obtained this red box, which is an HST ACS field, and constructed the corresponding CMD, which you see on the left of your screen. And you can see, crucially, that it extends below the oldest main sequence turnoff, allowing us to probe star formation back to the earliest epochs of the universe. And you can kind of do a star formation history by eye just by overlaying isochrones. So these are select isochrones from 10 million years all the way back to 13 gigayears. And I'm just going to focus primarily on the older populations. If you compare, for example, the red and the orange, you can see that at the main sequence turnoff, these are actually quite different. But as you ascend the red giant branch, they effectively overlap. And so while there is age information in the more luminous part of the CMD, it really is at the turnoff that these sequences separate out very nicely, and there's lots of age and metallicity constraint. And this is why such deep imaging is needed. And for galaxies this distant, the only way you can get so deep is with something like HST, which has high angular resolution and can overcome crowding or stars being very, very close together. So this is kind of a qualitative star formation history. And having modeled this CMD, I now show you a more quantitative star formation history. So what's being plotted on the x-axis is look back time, and on the y-axis is the cumulative star formation history. So that's the fraction of stellar mass formed at a particular epoch, normalized to today, where 100% of the mass is formed. And the reason we plot it this way is that you can then compare galaxies over a wide range of star formation rates without having to worry about the normalization between them. So to help you interpret these, because people don't typically look at these as much as I do, I've just plotted some very simple star formation histories. So if you had a purely ancient population, ancient star formation history, it would follow this red track, or a very young galaxy would follow this blue track. So most of the stars formed at late times, and a constant star formation history follows this green line. So to first order, the star formation history of IC 1613 is roughly constant, and then you can see there are some bursty features that cause the stellar mass to jump relative to that at various times. And so this is the example of the type of measurement we can make when we have such exquisitely deep color magnitude diagrams. So that's a little aside on the technique. Now let's get back to some of the science that this enables. I think one of the most important results has been applying this technique to ultra-faint dwarfs, so these very faint systems that were discovered by Sloan in the Milky Way halo. So this is a figure from Tom Brown's 2014 paper of 6 ultra-faint dwarfs that he observed with HST in the Milky Way halo. So you may recognize some of these, like Bootes 1 and Coma Berenices and Hercules. And these are very deep HST-based CMDs, and you can see just by comparison with this this empirical isochrone of M92 that they're all basically look as old as M92. So they're all ancient galaxies. And so, beyond just the qualitative star formation history this enables, Tom has quantified this, and so what I wanted to just show you what that looks like in terms of the plot. So this again is plotting look back time, although the oldest ages here are on your left to the youngest times on your right. And again, this is cumulative star formation history. And so this is the star formation history in blue of Coma Berenices from Tom's work. And so as you can see, basically this bulk of stars form very early. And then there's some, due to basically having a low number of stars, some probability that there's extended star formation to earlier time or later times or lower redshifts. But basically the bulk of the stars in this galaxy formed very early. For reference, this is the epoch of reionization on the same axes. And so the real takeaway is that Coma Berenices formed all or nearly all of its stars prior to the epoch of reionization. And this was the major finding of Tom's work. Now you can also take other galaxies from his work and plot them on here. So this is Hercules, slightly more luminous galaxy, but a very similar story, forming many of its stars, most of its stars, before the epoch of reionization. And here's Ursa Major, again, forming many of its stars before the epoch of reionization, but you can see that there is some tail to later times. And so there are many, many ultra-faints now, dozens of them, which we think have very similar stellar populations to this. They're challenging to characterize just because they have so few stars, but nevertheless, progress is being made. What I want to show you now is how these are distinguished from some of the more classical satellites you may be familiar with. So now I'm overplotting the cumulative star formation history of Draco, which is among the least luminous of the classical satellites. And so you can see Draco basically formed a smaller fraction of its stars prior to reionization and a larger fraction post-reionization. And as we go to more luminous Milky Way satellites, here's Leo 2, you can see that star formation, the bulk of it is delayed to later epochs. And if we go to even more luminous galaxy, Fornax, you can see that it basically had a constant star formation history. And so the basic trend you get out of the Milky Way halo are that more luminous galaxies tended to form more of their stars at recent times. And so this has really colored our picture of how low mass galaxies form. And I would love to fill out the rest of this plot but with 60 more lines, this becomes a little bit hard to see all these trends plotted this way. So created a summary plot. And just to orient you before plotting data, this is this summary plot of star formation histories. There's a little bit going on here, so bear with me. The x-axis is T50, which is the time at which 50% of the stellar mass forms. So you just essentially read this off the cumulative star formation history. And the y-axis, which I call the quenching time, is the time at which 90% of the stellar mass formed. And it's a good proxy for quenching. It turns out that in modeling CMDs, things like binary stars and blue stragglers make it really hard to nail down the quenching time, which would be T100 exactly. So this is a pretty good proxy. And plotted as these lines, these various styled lines, are different fiducial star formation histories. So for example, a constant star formation history would follow a track that looked like this in this particular space. And if you had exponentially declining star formation histories or tau models with various values of tau, they would follow either one of these tracks as indicated in the legend. So that's just the setup of the axes. And now we can just put on some of the Milky Way satellite data. So these are the Milky Way satellites for which we have measured star formation histories. They're color-coded by their luminosities, and the point sizes represent their half-light radii. And so just some broad takeaways that if you look at the faintest systems, they occupy the lower left region of this diagram. And so basically, they formed 50% of their stars early and then quenched very rapidly thereafter. And then as one pushes to more luminous systems like Leo 2 and Fornax, which I showed you previously, you can see that they formed 50% of their stars more recently and also quenched more recently. And so this is largely the broad trend that I described to you from the previous plot, only now supported by more data. And so this again is our fiducial baseline for understanding low mass galaxy formation, at least in terms of their formation histories. So one of the questions I brought up earlier was whether or not all low mass galaxies behave like this, particularly satellites. And this is one of the motivations for pushing towards M31, is to understand that if we were able to make these same measurements in another ecosystem, would they also look like this? And so one of the first adventures in this area was the initial star formation and lifetimes of Andromeda satellites, or ISLANDS program, led by Evan Skillman a few years ago. And this program obtained deep CMDs with HST of 6 M31 satellites over a variety of luminosities. I guess I've forgotten to list them here, but basically they go from about -12, which is Andromeda 2, down to -7.5, which is Andromeda 16. And you can see both the beautiful data quality here and also just the diversity of star formation histories. Just for example, by looking at the morphologies of the horizontal branch, you can see that, for example, Andromeda 3 has a weaker horizontal branch than others. And so that blue horizontal branch that tells you something about its ancient populations. Of course, again, we applied the CMD modeling technique to all of these galaxies and measured star formation histories. And so these are the star formation histories of those same 6 galaxies from the previous slide, from the Skillman et al. Program. And what you can see is, again, they span this wide range of luminosities, so 5 magnitudes in absolute magnitude. And you can basically see that they have actually quite similar star formation histories. And in fact, some of the trends you see are even slightly different than one would expect for the Milky Way. So for example, Andromeda 16, the faintest system, actually appears to have the most suppressed star formation at early times, instead of just quenching early as one might expect. Whereas others like Andromeda 2 or Andromeda 3, they just are kind of all bunched together. And then also interesting is that they seem to all quench around a similar epoch, roughly redshift of 0.5 or 5 to 6 gigayears ago. So just to elucidate this a little bit more clearly relative to the Milky Way satellites, we can go back to this T50 versus T90 plot. So on the bottom, I'm showing the Milky Way satellites as you've previously seen, and the top are the 6 Skillman et al. Satellites that I've shown you previously. And just qualitatively comparing them, you can see that these M31 satellites occupy a region of this diagram in which there are essentially few or no Milky Way satellites. So this was already fairly interesting, but again, it's only 6 galaxies. And so the idea was we really needed to push on to get more. Of course, it's very expensive to get this data. I think the Skillman et al. Program ended up being something like 120 or 130 HST orbits. So concurrently, Nicolas Martin and I had a smaller program going with HST, which was simply to get sub-horizontal branch imaging of the remaining satellites as kind of an exploratory exercise. So what's being plotted here are the 17 Andromeda satellites we got as part of this program. The most luminous are being shown in the upper left, down to the least luminous in the lower right. And just to give you a sense of the luminosities, I mean, minus 6.1, this is Andromeda 26. The CMD is a little bit messy, especially to the untrained eye. But basically, we're looking at a bona fide ultrafaint at about 800 kiloparsecs. And so we're actually able to get some handle on its stellar populations. Similarly, things like Andromeda 20 are quite faint, and we can see there's a nice horizontal branch, red giant branch here. And we can get course age estimates by modeling these CMDs and just to see if there's anything interesting there. And so this was going on at the same time as the Evans Deep program and allowed us to just explore without committing too many resources initially. So here is the resulting star formation histories. I've actually flipped it so that the least luminous galaxies are in the upper left and the most luminous galaxies are in the lower right. And you can see the luminosities are indicated again in each panel. They're actually changed slightly because we found out from the horizontal branches we had some distances wrong and have corrected that since. And you can, I could spend a lot of time talking about this figure, but I think it'd just be easier to look at it in the frame of T50 versus T90. So one thing I'll note before I do that is if you look at the error envelopes around here, these gray bands are the statistical uncertainties just from the number of stars available on the CMD, and these purple or blue bands indicate the variance in the star formation history due to the stellar model library use. We used several different stellar libraries just to see how much the star formation history changed. And indeed, it's the predominant source of error when you have such shallow CMDs. And this is actually the motivation for going even deeper. So going back to the T50 versus T90 plot, again, the Milky Way satellites are in the bottom panel. The upper panel shows the Skillman et al. Satellites. And now we can add in the results from this work that Nicolas Martin and I have done. And so now we have about 25 M31 satellites with varying quality star formation histories, but it allows us, at least for the first time, to put on the M31 satellites on the same axes in terms of formation history as the M31, as the Milky Way satellites. And so you can just by eye see that there are some broadly different trends here. For example, if we look at the M31 system, there's a number of satellites that follow this track. This is an exponentially declining star formation history track with a tau of 2 gigayears. You can also see we don't have this pileup of galaxies in the lower left-hand corner. Presumably, this could be due to selection effects. It's just very hard to find faint galaxies around M31. But even some of the fainter galaxies that we have found around M31, these orange points, don't tend to pile up around here. And so that's already kind of interesting. Of course, the error bars are large, so we have to be cautious at this point. But it's already kind of an interesting find. Another interesting thing you'll notice is that if I just highlight this region of this diagram, this blue box, you'll see that roughly, I think, half or even 2/3 of all the M31 satellites have quenching times between 3 and 6 gigayears ago. And if we look at the Milky Way halo, we simply don't see that. There's just nothing in this box. And we know, at least around the Milky Way, there is nothing here. Around M31, of course, we know that there are several galaxies here. Some may shift in and out just due to the error bars, but nevertheless, a large population exists there. So, these are the measurements. Now, understanding why they're different, of course, is the really interesting question. And we can go, I'll share a favorite interpretation with you, but I think we're far from really understanding what the genesis of these differences are. So this is an image many of you may be familiar with. This is from the PANDAS survey, which mapped out basically the stellar density of M31 out to 150 kpc and was responsible for discovering virtually all of the dwarf galaxies around M31. But what you really, what I really want you to take away is the substructure. So you can see all these streams. There's a lot of points here, which are either dwarf galaxies or globular clusters. Just more, shell features, things that we, have been known for a long time, but we don't really understand their provenance. The thing, the generic conclusion from this and the consensus is that M31 has just had a more active recent accretion history than the Milky Way. And this is the cause of this substructure. And this, the nice story is that it may also be imprinted in the satellite population. So I will pitch you one of the possible stories here, which I tend to like. There's this paper by Richard D'Souza and Eric Bell from a couple of years ago that hypothesized that M32, so many of you may be familiar with M32 as this kind of bizarre, extremely compact galaxy that we don't really understand how it got that way. That M32 is actually the stripped remnant of a more massive galaxy, something that was within a factor of 2 mass of the Milky Way, and that actually merged into M31 a few gigayears ago. And so it's really interesting. I'll just explain their scenario and talk about how it may connect to the satellites, but it's interesting to think that several gigayears ago, we actually may have had a third massive galaxy in the local group, both from a local group standpoint in terms of how it evolved, but more broadly what that means for our cosmological understanding of the local group. So the D'Souza and Bell story goes a little bit like this. 4 gigayears ago, you had M32P, which is at some distance, about 90 kpc from the disk of M31. So this red circle is the disk of M31. And you can just see that it's coming in closer and closer as time goes on until about 2.5 gigayears ago, it interacts with the disk. And then you can see the creation of these streams and these shell features. And they queried, this is using Illustris, so the resolution isn't great, but they queried ages of star particles in here. And you can see that there is generally, what they call star formation shutdown times in terms of gigayears ago, of something like 3 to 6 gigayears ago for many of the star particles in this simulation. And so the next part of the story might be to say, well, if you had a galaxy that was almost as massive as the Milky Way, it probably brought its own satellite population with it. And could the process of accretion onto M31, or this interaction, have transferred the satellites? So now perhaps some satellites of M31 were once satellites of M32P. And could they also have shut down because at similar epochs? So keeping in mind this 3 to 6 gigayear ago number, if we go back to the M31 satellite plot from the star formation histories, again, there's a large population that also shut down in this time range. Of course, this is all tentative. This is very speculative theoretically. The error bars are large for many of these systems in terms of measurements, and this is because we have shallow CMDs. But it's this type of argument that motivated the fact that we do need to study systems beyond the Milky Way halo, Milky Way satellites in such detail, because it could be we're just looking at a special environment around the Milky Way. And so this was one of the motivations for this Cycle 27 HST program that I'm leading, which is a roughly 250 orbit survey to get deep color magnitude diagrams of the 23 faint M31 satellites that we know of that don't have deep CMDs, as well as incorporate 10 galaxies from the archive with comparably deep CMDs to do a homogeneous star formation history measurement across the M31 system. So we're obtaining this imaging. I'll show you some of the early data in a moment. This is a program that I put together with great input from Nitya Kalibayalil and Andrew Wetzel, who both have interests in the proper motions this will enable, as well as the theoretical implications. So the main science goals are to measure star formation histories and the age metallicity relations from deep CMDs, to map out precise distances to all the dwarf galaxies, including the faintest ones from our Lyrae. So we have good cadence for our Lyrae sampling. And the images we'll obtain will allow for first epoch of proper motion measurements to be followed up with either HST or JWST in 5 to 10 years, and doing other science like understanding how the horizontal branch can be used for improved star formation history determination. So some of the early work from this program, these are very new CMDs. We've just been able to take data on the first 6 galaxies last fall, and the remaining are coming this coming fall. So these are CMDs for galaxies that are as faint as Andromeda 26, so minus 6.1 in terms of luminosity, all the way up to Andromeda 6. And you can see the quality of the data is exquisite. We get some really deep, beautiful CMDs. I'm not going to, we don't have preliminary star formation histories yet, but I will highlight just some interesting features. If you just look at the horizontal branches, starting with Andromeda 26, you can see what's interesting is it has a blue horizontal branch and it has a red horizontal branch. And you can get a red horizontal branch either in a few ways, but typically or often it's with a younger population, so potentially post-reionization, and that would be interesting for such a faint galaxy is to find bona fide star formation post-reionization. But you can also see if you look at something like Andromeda 33, it basically has no blue horizontal branch. So it means it could be an entirely young or youngish galaxy. And so this is basically where we are now, is just reducing the data and looking at the very qualitative star formation histories as we gear up for the really the big round of data that's coming up over the next about 6 months or so. So I just want to summarize what I've talked about and then just dive into a little bit of what I think the future steps are. One is that, I think that we should appreciate low mass galaxies as a unique window into a number of important topics such as dark matter, cosmic reionization, baryonic feedback, and galaxy formation. The question that I've been thinking about a lot lately is just, are the Milky Way satellites really representative of low mass galaxies or satellites in general, and what does it mean if they're not, or how concerned should we be about some of the conclusions we've drawn? And I think that the M31 satellites are already showing signs of systematically different formation histories than the Milky Way satellites, with the caveat that we are just getting the deep data now. And that was the purpose of the Cycle 27 Treasury program. Looking into the future, I think some of the important things beyond just what we're doing with HST will be to identify even fainter galaxies around M31. We really want to push the limit of what we can find and study, and also to obtain deep CMDs of faint galaxies beyond the local group. So just to put this into visual context, this is a plot showing all galaxies in the local volume, so within a radius of 10 megaparsecs of the local group. And so for context, this is the local group. So everything I've been talking about has been conclusions based on galaxies within the circle. And to get a deep CMD beyond the local group with HST is 100 to 150 orbits. It's just prohibitively expensive and basically, for all practical purposes, impossible. So as part of the motivation for the JWST ERS program that I'm leading, one of the things was, can we start to push star formation history work outside the local group for the first time ever? So if I show you what we can do, so what I've color coded here are galaxies for which JWST can reach the oldest main sequence turnoff with 100 hours of integration. So these are impossible to reach with HST and expensive with JWST, but out to about 2 megaparsecs. This is in terms of projected distance, but in 3D distance out to about 2 megaparsecs, JWST can reach the oldest main sequence turnoff. So it'll allow us to push into a non-group environment for the first time ever. And so just to briefly talk about the early release science program, just if you look on the right, this is an example of a simulated color magnitude diagram in the JWST filters F150, so roughly 1.5 microns, and F90 minus F150. So basically the whole wavelength range has just shifted into the near infrared, but all of the same features are there. And in fact, you get a slight boost because the oldest main sequence turnoff, basically all the red stars like the turnoff and red giant stars actually become brighter in the near infrared, so it becomes easier to access them. So the purpose of the ERS program was to enable this type and other types of science because JWST can do resolved star science to larger distances, to lower stellar luminosities in regions of higher extinction and in more crowded regions than anything else including HST. This is a very information dense slide, and since this talk is being recorded, I decided to include it because people can go back and look at it, but this is the main detail of the ERS program. So the idea is that we're using NIRCam as our primary, so those are the kind of blue hash mark squares here, and the nearest module in parallel to obtain imaging of 3 objects. One is globular cluster M92, one is ultra-faint dwarf galaxy Draco 2, and one is distant star-forming galaxy or dwarf galaxy WLM. And we have a variety of science reasons for going after each of these, but largely they allow us to calibrate JWST performance in a variety of environments that are going to be common use cases. And of course, the delay of JWST means the exact ERS window could change, and so we might have to change targets, but this just gives you a sense of the types of objects we're going to use to do this calibration. And so what do I mean by calibration? Well, our main deliverable is going to be building and disseminating crowded field PSF software to the community using JWST specific PSFs, much like we've done for HST and now a team that I'm working on for WFIRST. We're going to calibrate the JWST ETC for PSF photometry. This actually was an issue early on with HST, that the ETC was good for aperture, but not PSF photometry, which kind of skewed the exposure times. We'll provide matched JWST and HST source catalogs for all the ERS targets, and also provide easy to follow examples for how to reduce data, perform PSF photometry, apply it to science, and plan observations. Because JWST is a limited lifetime mission, we really want to provide as many, make using it as easy as possible for people who are interested. I've only given you some details, and earlier last, I guess 2 months ago now, I gave a ERS webinar for Space Telescope, and I've included a link. You can go watch the entire webinar where I describe the ERS program in a lot more detail. It's also, you can just find it on Google. This program is something that I'm leading. There's a number of highly, very talented people who are doing technical development of the software. We have 6 science teams that are exploring science enabled by the ERS observations, from star formation histories to the low mass IMF to measuring proper motions. And so all of this is being enabled by the same set of observations of these 3 systems. So just to go back to where JWST will take us, these color-coded galaxies are where we think we can reach the oldest main sequence turnoff with JWST. Of course, since it's the time of the American Decadal Survey for Astronomy, we've been thinking even more about the future. So a proposed concept mission like a 4-meter class UV optical space telescope would extend our ability to obtain such deep CMDs or main sequence turnoff depth CMDs out to about 2.5 or 3 megaparsecs. You can see those in the color-coded galaxies here. And the even more ambitious mission being considered would be a 9-meter class space mission, and that would enable the CMDs out to about, deep CMDs out to about 5 megaparsecs. So now we're talking like hundreds of galaxies, many hundreds of galaxies, and the most ambitious mission would be something like a 15-meter space telescope. And that would basically enable deep CMDs and the type of work I've described to you throughout the entire local volume. And so I think this is all I wanted to share with you today, and I will take your questions. Thank you.
Thanks very much, Dan.